Welcome to the satellite communication course. So today we'll learn that what are the various antennas present on a satellite, or we want to know about that what are the various that antenna control system. So that we have to see. So we'll learn that how to control the antenna parameters and all, and we need to know about the what are the various parameters. As we have seen the antenna parameter in last lecture, we continue with the various types of antenna and that antenna used in a satellite communication for uplink and a downlink communication. And the same antennas that are used for the communicating to the earth station regarding their position of the satellite. So now, first of all, we start with a antenna, and that antenna work for what applications. So if you consider that a antenna in a satellite present, they have the horn antenna, they have the reflector antenna, and along with that, they have the dipole. Dipole. Now, if you see that all the antennas, this one horn antenna and reflector antenna, it produces a unidirectional radiation pattern. But in the case of a dipole, it produces a omnidirectional radiation pattern. Now that radiation pattern, whether it will be unidirectional or omnidirectional, that depends upon that what type of an antenna we are using. So now, if we say that unidirectional means what? For a given direction that antenna is to be worked, and omnidirectional means it is radiating signal in all the direction. So that's why sometimes the dipole antenna is again we are saying that isotropic radiator or a isotropic radiation antenna. It radiate signal in all the direction. But in omnidirectional means what? It is a one plane. It radiates the signal in a one plane. Now there are the various types of horn antenna, and that antenna used for the satellite communication. But if you consider the antenna here, horn antenna, so in that case we can consider that for a complete coverage or a global coverage. And if you consider that reflector antenna, that will be used for the spot beams, or we can say that it will provide say multiple beams there. So we can say that a multi beam, or we can say that is about a spot beam, and you can say that this is about a all coverage, or we can say that is about a global coverage here. Now horn antenna that will be useful for the global coverage. Now if you consider that a global coverage and a radiation pattern of an antenna, so it is we say that is about a unidirectional one. So radiation pattern will be a unidirectional. That is for the horn antenna. And here we say that a word is about a global coverage, which only single beam is generated, and based on that a beam width, we can say that there may be the area coverage by the given antenna. So area coverage of the antenna, it is depending upon that how we are focusing the antenna, or what will be the gain of the given antenna. In that case, we need to know about the size of the antenna. So in a horn antenna, we need to say that size is nothing but a aperture area or a aperture height of the antenna here. So what will be the aperture area of this horn antenna? So for that purpose, we need to know about what is the structure of a horn antenna. So there are the two types of a horn antenna. One it we can say that their aperture is in a rectangular form, or we can say that it will be in a circular one based on the aperture. So rectangular horn, they are use a rectangular waveguide. With that waveguide, mouth is open to one end, and they are flared to make that shape of what you can say that is about a pyramidal shape, or you can say that that shape may be of a cone like a structure. So in that case, that one end is a cone like structure or a shape of a pyramid, or a we can say that that will be nothing but a in terms of a rectangular shape. So they are according to that they are a two types of an antenna, that is about a you can say that pyramidal horn antenna, or you can say that a circular horn antenna. And that is about pyramidal horn antenna, or we can say that is about a circular horn antenna. In the case of a pyramidal horn antenna, we should know that basically what do you mean by waveguide? Waveguide is a structure, it guides your signal propagating okay through this structure here. So it is about a hollow metallic structure, it guides your signal and it propagating your wave through this rectangular type of a structure there. But in the case of a horn antenna, so that rectangular shape is flared, that one end it that one end is shaped with a structure like a pyramid or a structure like a cone here. So that will become a pyramidal horn antenna or a circular horn antenna. Now I'll draw first how your pyramidal horn antenna will be looks like. This one is about your rectangular shape we say, and here for this a height here. You can say that draw here first so that it will be easiest to us. Okay. So likewise we have the rectangular shape of the horn antenna. Okay. Now this is nothing but what we can say a rectangular horn antenna. Okay, that is about a pyramidal shape. I think this one is larger now, but it is about a rectangular shape. That is called as a pyramidal horn antenna. And in the case of a circular one, that end is a circular one. Okay, here we can say that that end of this forms a circular here. It may be a circular waveguide or it can be a shape of a square can be converted into a conical form. Okay, so that it will give us the circular shape of an antenna. This one, this is about a circular shape. That is about a end is a circular one. So if you consider that a output of this is nothing but a plane wave, it is nothing but a plane wave for this a pyramidal horn antenna. And if you see the radiation pattern, it has only a single lobe. It has only a one main lobe, just like it has only a one main lobe. No back lobe, no side lobes will be there. In the case of a circular one, so that output of this circular horn antenna is a circularly polarized wave. It is called as a here we can say that it is about a circular horn antenna, and the output is what it is about a circularly polarized wave. Okay, it is nothing but a circularly polarized wave. That is about the antenna, that output of the circular horn antenna. But in the case of a pyramidal horn antenna, it is just like a output is nothing but what it is a wave front is plane wave, and output is about a a linearly polarized wave. Okay, that is about a linearly polarized wave. Means we can say that either output is a vertical polarized or a horizontal polarized. But in the case of a circular horn antenna, output will be a circularly polarized, in which there is about the right hand circular polarized wave or a left hand circular polarized wave. And this shape here we can say that is about this particular rectangular shape or this particular circular shape, that is about the aperture. Based on the size of that aperture, that gain of the antenna will be increase or a decrease. And then again, a number of modes produced by this horn antenna or this particularly that circularly polarized horn antenna, it is depending upon that what coating we are using inside this particular horn antenna. So now this two antenna they can generate the higher order modes if we use a coating. So if we use a higher order mode, then what happen? That will reduces the cross polarization there. So that's why internal structure of that particular horn antenna or circular horn antenna, they are they have the corrugation inside, or we can say that inner surface they are corrugated here. So that's why they are generating the higher order mode. And then because of that higher order mode, so that they reduces the cross polarization. And that radiation pattern we are getting, that is about a unidirectional one, and we can say that according to this aperture size, we are getting the high gain of the antenna there. So in this case, we need to know about what will be the flare angle, because the end of the waveguide, if you see that it looks like here, okay, it is nothing but a flared one. So that's why based on this particular flare angle, that is about we say it is about a theta here. According to that, your gain, or you can say that a directivity will be changes. So we should know that for a given particular antenna, so what will be the directivity and what will be the gain. So we should know that a flare angle as well as the what will be the aperture size of that antenna there. So as I told you earlier that horn antenna is useful for the global coverage. Okay, we say that it is to be used for the global coverage. So in that case, so it's supposed to be we are using the antenna. Okay, so from this particular satellite. So now this is about a radiation pattern, or you can say that this must be the coverage by the horn antenna. This is about the region, or it is nothing but the coverage by this horn antenna. So in that case, what will be the beam width? What will be the beam width of this particular horn antenna? So to understand the beam width, we should know that what will be the sub-satellite point. Okay, what will be the sub-satellite point? Means it's supposed to be this about a antenna here. So from the satellite, we say that this one is about the antenna. We say, and this one is your radiation pattern. So beam width is depending upon that. What will be the main lobe or where we are getting the maximum? So maximum is nothing but a sub-satellite point. This is nothing but a sub-satellite point, or you can say that sub-satellite point is nothing but a perpendicular from the center that satellite to the Earth surface. Okay, that is nothing but here we are getting the maximum there. So that is about it. From this, we can say it is about a sub-satellite point. So around that, we need to find out the beam width here. So that is the beam width is likewise. So we can say that this one is about the coverage for this horn antenna, and this particular theta, we say that it will be used for the global coverage. So in that case, the beam width will be a 17-degree for the global coverage, and that beam width will be aligned to the sub-satellite point. Okay, that will be aligned to the sub-satellite form. So then we can say that we say that that will be work in a global coverage there. And then again, we say that again we say, or you can say that is about a directivity. So maximum power delivered in a given particular direction. So that will give you the directivity. So in the case of supposed to be antenna is vertical now here at the center or at that particular point, you can say that we are getting the maximum gain, or you can say that a maximum output. So that's why that directivity toward this particular direction it will be a maximum there. And this horn antenna is used mostly as a feed for the reflecting antenna or a reflector there. So reflector type of an antenna means just like we have the a shape of what we can say is like a shape here, and in this particular case we have the antennas, maybe a dipole antennas or maybe a horn antennas are there, and that shape that will be useful for the reflection. And this, okay, all these antennas are on the same axis, whether it will be dipole or a horn. In that case, that will be called as a array antenna. If it is only a single feed antenna, just like we have seen earlier, we say earlier that is about a dish antenna we have, and there is a feed that is about the horn antenna is there, and this one is nothing but a dish here. And then radiation from this horn antenna, okay, signal from this horn antenna, your signal will be radiated in a space likewise. So this is about your wavefront. So now this one is a single reflector antenna that is used. If we say that a multiple horn antennas are used, single horn antenna here. If we are saying a multiple horn antenna, then the structure is called as a array. Here this one is about a reflector shape, and in that particular reflector, they are using a multiple antennas. So that's why the reflector array antenna. Okay, it can be a dipole or it can be a of a horn there. So means single reflector we have, this one is about a nothing but a single reflector here, and for the single reflector there are the multiple horn antennas are used, so that it produces a different radiation with a single beam or a multiple beam. Which we say that earlier, that is about a spot beam. If we have the single radiator, so it will produce as a single beam. Even if there are multiple radiator, multiple, we can say that a feeding element, they may be on and a dipole. So it can produce as a single beam or it can be produced as a multiple beam. So that if it produces a single beam, so in that case, a coverage will be increased. Then we can say that a gain will be increased. Again, we can say that is about a directivity will be improved. But in the case of if it is a multi-beam, if it is a multi-beam, then coverage, okay, that coverage will be increased. But then there will be the reduction, or we can say that your gain and directivity may be reduced here. But in general, why these reflector antennas are used in a satellite communication? Because we need to get that output high, or you can say that it produces a, or it delivers the high gain, and they have the narrow beam. Because of the narrow beam, that gain will be increased. So narrow beam means what? Directivity again increases. So generally, a parabolic structure is used as a reflector, or a paraboloid is used as a reflector there. In the case of a reflector antenna. So now this is about a fact about the reflector antennas that is used in the satellite communication. They have the high gain or they have the narrow beam there, and they are using a parabolic structure, or you can say a paraboloid, that will be placed at a center. Okay, that horn is placed as a center, and this is nothing but a parabolic structure. Horn is placed at the center or a focus point, so that incoming rays are focused at this particular point, or we can say that outgoing rays will come from this particular focus point, so that we'll get that antenna to be work at a transmitting or a receiving there. Suppose in the case of a receiving, all the incoming rays are reflected from this reflector, that is parabolic structure, and all they are focused at the particular point. So that is about the incoming rays. But in the case of a transmitting antenna, all the rays are coming out from this horn antenna, and they will be reflected from this reflecting structure. That is that's why we are saying that here it produces a narrow beam. Narrow beam means what? If that parabolic structure, okay, if it is narrow here, or you can say that if you design a structure in such a way that we'll get that a narrow beam here. But in a reflector antenna, they have the cylindrical half cylindrical structure is there, and at the center of or axis of that particular cylinder, that antennas are placed. That will be dipole antenna or horn antenna. So that it produces the multiple beams there. Okay, it produces the multiple beam. But in the case of this one, single one, only that only one antenna will radiate the signal in space, so that it will produce a single beam, and coverage will be depending upon that a single horn antenna or a single parabolic structure. Even if we increase the size of the dish or that parabolic structure, so that may improve that. Okay, that may also improve the gain or a directivity. So that is about a horn antenna if we use a single or a multiple one. But if you case here, so if we use a multiple horn antenna, then gain will be increases there. So that's why we are saying a reflector antenna, they have the higher gain and a narrow beam. So narrow beam or higher gain, that will give rise us the way that single beam, spot beam or single beam or a multi beam there. So parabolic reflector, we say that it produces that is about a plane wave here, and we are getting the plane wave output. But in the case of, as we say earlier, that is about a rectangular horn antenna or a circular horn antennas are used. That is for the feeding one. But output of this is a linearly polarized wave, and here it is about a circularly polarized wave. Okay. But if we consider that if feeding here as a rectangular horn antenna, then we'll get that output is nothing but a linearly polarized output here. Okay, that output is nothing but a linearly polarized output. So depending upon that a size of a horn, and depending upon that parabolic structure or that aperture of this particular parabolic antenna, your gain will be improved there. So there are different types of a parabolic antenna or reflector antenna. How we are feeding, there are the various feeding techniques. Here, that horn antenna is placed at the center or at the axis or a focus point here. That's why it's called as a center feed horn antenna. Okay, or you can say that on axis horn antenna. If we place that horn antenna instead of at that particular center or axis, so then we can say that is about the off axis horn antenna. So feeding how we place the horn antenna, whether it is at a center or it is a off axis there. So according to that, that gain will be improved there. But if we consider that a offset fed antenna, they have the advantages with respect to the thread fed antenna, because offset fed antenna, that is nothing but at a center, it will be here. Okay, if it is offset feed, so it will be horn antenna will be here, and that then will they will focus the signal in a given direction. That is about a offset feed antenna. But in a center feed antenna here, it will be present here at a center, so it will focus the signal in the given direction. So now why this offset feed is good? Because this horn antenna will not come in a line, or it will not come in the line of a transmission there from the reflector. But if means what? Here's now center feed antenna here. When it transmit the signal from the horn antenna, it will be reflecting from the reflector itself. So then signal will be transmitted towards outer side here. So in that case, this is nothing but a line of transmission. So this horn antenna is coming in the line of a transmission. So that's why this one is nothing but this area or this particular region is nothing but a blockage. Okay, this nothing but that region is nothing but a blockage for the transmission here. But in the case of offset feed antenna, it is about the offside here, offset here, not on the same axis there. In that case, so offset feed antenna, so it is placed here likewise. So it will transmit the signal to the reflector line likewise, and then it will be propagating likewise. So in that case, this is about a line of transmission. This one is nothing but a line of transmission. So in the case of a line of transmission, this iron antenna is not coming. So it will not block that whatever the signals there. Means it will not block that reflected wave from the parabolic reflector. So that's why the overall efficiency of that antenna will be improved. So if it is a offset feed antenna. But in the case of a center feed here axis antenna, so in that case, so this antenna will be act as a blockage here. So that's why they might have reduced that's why they are reducing the efficiency. They are reducing the efficiency of the horn antenna. So parabolic shape or a circular shape that can be used. So various shapes can be used, and that shapes can be used as a reflector antenna. Okay. So various shapes we can say that. Just I told you earlier. This one is about a cylindrical shape here, half cut cylinder here, half cut paraboloid or half cut cylinder here, that is used. So this type of antenna that produces a multiple beam or a single beam there. So how we design a structure, or what will be our output, whether we are interested in a single beam or a multiple beam. So according to that, that various types of structures can be used. So if we want a shape will be of a circular one, or we want a shape in a different way here, that type of different type of structures can be designed there. So if we have a single aperture, they can also create the multiple beams when we have the multiple horn antenna. Okay, so we are learning here, or sorry, reflector antenna. Now, as I told you earlier, if we have the single aperture, if we have the single aperture, that single aperture can create the multiple beams. It will create a multiple beams when we have the multiple horn antenna. When we have the multiple horn, as we can say, it can be used as a feed here or a feeding system. So in the satellite communication, so multiple beam antennas are used that will be useful for the mobile communication or a mobile, or you can say that a satellite mobile communication, then that will be used in a LEO orbit satellite or a LEO orbiter. So to get the circular aperture of the given antenna, then the gain of that antenna, that is to be G is equal to, here we have the aperture efficiency of the given antenna with respect to what will be the area here and at what will be the operating wavelength there. So this one is nothing but what, a aperture efficiency of the antenna here, and that A is nothing but the aperture area, and this wavelength, we have the operating wavelength of the antenna there. But this aperture efficiency means, as I told you earlier, because we have the blockage here, okay, or this horn antenna is connected likewise with a metallic structure, the signal which come in line, that block, that metallic object will come in a line. So because of that, signal may be reflected from it, or that focus of the given antenna, there is nothing but a horn antenna here, so it is present at the center now, like we have the horn antenna here. So signal will be come from this horn antenna here likewise. But what happened, because of that size of this parabolic or a circular dish is a small, so in that case signal may be go outside here. Okay, signal may be go outside, and that particular signal, or that particular or that particular range of a signal is nothing but what we can say, a spillover, or you can say that because of this particular, this is nothing but a spillover, or this horn antenna is nothing but used as a blockage here. So blockage, so this antenna efficiency is depending upon that what will be the spillover or what will be the blockage there, and again it will be depending upon that what will be the cross polarization in this particular antenna there. So generally we say that this efficiency of this antenna, or you can say that aperture efficiency, is nothing but the product of what will be the rays are reflecting from this, or illuminated ray from this particular reflection there. So you can say that a illumination here, illumination efficiency. Again we say that it is nothing but a spillover efficiency. Again it will be depending upon that what will be the blockage efficiency. Then it will be depending upon that how much will be the reflector surface efficiency. Then we are feeding this antenna, so what will be the feed page errors. Then what will be the cross polarization efficiency, and what will be the mismatch efficiency. So based on that, we can calculate that what will be the aperture efficiency of the antenna for a circular aperture. But if you consider that a circular shape, that will be the area or a parabolic area, so according to that we are getting the efficiency. But if we are writing that gain of that antenna in terms of the diameter here, so in that case a gain will be equal to aperture efficiency and that pi d, that is about the diameter of a dish, or you can say that is about a circular shape here, and that will gives us the whatever the gain of the antenna here. Now these are about the efficiency, all this factor here. So if we consider the horn antenna, so in that case the illumination efficiency, how much will be the illuminated ray from this, is to be considered, as well as the what will be the spillover is there in the antenna there, and how much will be the blockage is there. Because spillover is there, blockage is there, illumination from this is there. So that's why that efficiency, aperture efficiency is depending upon this three factor. If we are using the horn antenna, if we use the instead of a center feed, if we use the offset feed, then blockage will be reduced. Okay, if we use the offset feed instead of center feed, then what happen? The blockage efficiency will be reduced for the same input and all. So how we are using that antenna, and then for what particular purpose, and or which direction we are using that antenna, according to that, that each and every factor of the efficiency is to be considered there. And the beam width for the antenna, that reflector antenna, or you can say that the 3 dB beam width of an antenna is approximately equal to, we say that it is about a 75 lambda divided by d, that is in a degree here. This one is about the beam width of a radiation pattern, because likewise if you see that this one is the radiation pattern of an horn antenna, and here is we have the maximum output. So from this maximum we need to locate the 3 dB point, and from that 3 dB point we need to calculate that, draw the line from the center to the 3 dB point, we will get that this is nothing but a 3 dB beam width of an antenna, and it is depending upon that what will be the diameter of the aperture, because we have a circular dish or a parabolic dish. So which structures we have. So according to that, what will be the diameter of the aperture, and what will be the operating wavelength. So beam width is the factor depending upon the both the parameters. Then next we consider here what are the other parameters produced by this, or we can say that that is to be utilized in the satellite here. That will be nothing but the multi beam. As I told you earlier, that multi beam produces by the reflector antennas if we are using the multiple horn antenna. But what is the necessity of a multi beam antenna? Because on the earth station, or because on, or we can say that about the earth here, there are the multiple earth station. Okay, they have the multiple earth station. So that each and every multiple earth station, we have the satellite that transmitting the signal. So What will be the area coverage by this? Likewise, this is about the coverage area of the satellite, and this is nothing but that in this region. This one is nothing but a beam here produced by the particular antenna here. So means different receiver at the earth station. Here we can say that a earth station, and there are the different receiver, multiple receiver at the multiple places there. So means that antenna, that radiation will be of a multiple one. So in that case, for the antenna, they have the different uplink we say earlier, okay, or you can say that a different downlink here. So means they are utilizing that multiple carrier means satellite, and we work for the multiple carrier, and they have the different uplink and a different downlink. So multiple carrier means what? We have the multiple transponder, just like we said that a bent pipe transponder, and that bent pipe transponder they are used for the conversion of the uplink and a downlink signal there with a given particular requirement for the earth station there. So or in a given transponder, your signal will be processed and then it will generate that particular downlink signal, and then it will be transmitting there. Means incoming signal from the earth station to the satellite. Okay, means they are the different earth station signals are, okay, that is nothing but incoming signal to the satellite. So they will be modified or processed, and then that will be converted to the onboard processing transponder, and then they will be transmitted to the earth station there. Because of multiple earth stations, so in a transponder, that signal selection is used, or you can say that a band pass filter, or you can say that one baseband structure is to be used to select that particular signal, so that a multiple beam antenna will produces the multiple multiple spot or multiple coverage for the given earth station there. So that's why I say that a number of beams are depending upon that how many number of a reflectors we are using. So if we are using a multi beam antenna, so multi spot here, so that's why a frequency reuse can be done using the multiple beam here. So means one beam can be used here for the one application, another beam is used for the another application. Likewise, we have the multiple beam is used for the same frequency but multiple beams are there. Okay, so just like we can say that multi beam antenna, they have the multiple reflector antenna. Means from this we say that frequency reuse technique can be effectively used if we have the multiple beams array. We can say that we have the different earth station they are used for the different same operating bandwidth or same frequency there. Okay, so that's why I can say that if frequency reuse using the multiple beam antenna. So that's with about your antenna we have learned. So in this case, we consider that effective use of a frequency reuse using the multiple beams in the given available bandwidth here. Because earth stations, if you say that they are geographically separated. Okay, they are geographically separated. So that's why, because of that separation of the Earth station, so frequency used by the one beam, this is about a frequency used by the one beam, that can be same frequency can be used by the another beam. Okay, so that's why it is called as a frequency reuse, the satellite there. So as I told you earlier, there may be a multiple on antenna is to be used. So similarly, if we have the dipole antenna, or you can say that omnidirectional antenna, so it produces that dipole antenna produces the omnidirectional radiation pattern. So generally, dipole antenna is nothing but a linearly isotropic radiator, and in a reflector antenna, if we are using the dipole instead of horn antenna, so even if that will produce the multiple beams there. But that dipole antenna or omnidirectional radiation pattern is used in a TTC command. So we need to control with respect to the earth station there, telemetry tracking and a command system subsystem. So in that case, a omnidirectional radiation pattern or omnidirectional antenna is used. That is nothing but a dipole is used.